What if the internet was unhackable? I mean, completely and fundamentally unhackable. Not just difficult to break into, but built on laws of physics that make snooping impossible. Imagine sending a message, a bank transfer, or a state secret, and knowing with absolute certainty that no one else could ever intercept it. This isn't just a fantasy from a science fiction movie. It's a real possibility that physicists and engineers are building right now. It goes by many names, but the most exciting one is the quantum web. A new kind of internet that doesn't just promise better security. It promises perfect security, guaranteed by the universe itself. This new internet won't be built on the same foundation as the one we use every single day. The classical internet, the one you're on right now, sends information using bits. These are simple on or off signals, ones and zeros, flowing through fiber optic cables, bouncing off satellites. But these signals can be copied. They can be intercepted and read without a trace. The quantum internet is different. It uses the strange and mind-bending rules of quantum mechanics to send information. It's a network that operates on a level of reality so weird, it almost sounds like magic, but it's very real science. Picture this. A single satellite glides silently through the blackness of space, high above the curve of the Earth. It's not beaming down Wi-Fi or GPS signals. Instead, it's firing a single fragile particle of light towards a ground station. This isn't just data. It's one half of a connected pair, linked to another particle hundreds or thousands of miles away. They are connected by a bizarre phenomenon called quantum entanglement. What happens to one instantly affects the other, no matter the distance. This invisible, unbreakable link is the key to building an entirely new communication infrastructure for our planet. This is not a small upgrade. It's not like going from 4G to 5G. This is a fundamental shift in how we connect with each other. The stakes are enormous. We're talking about a network that could be faster, more powerful, and exponentially more secure than anything that has come before it. It has the potential to transform everything. Global finance, national security, scientific research, even the way you message your friends. The quantum web could create a future where digital privacy isn't just a setting you turn on, but a fundamental property of the network itself. It's a huge idea, and it's happening faster than you think. So how does it all work? You're watching Apex Tech, decoding the tech that's building tomorrow. The physics behind it can sound complicated. Words like superposition, qubits. But the core idea is surprisingly simple when you break it down. Over the next few minutes, we're going to peel back the layers of this next-generation technology. We won't just talk about theories. We'll look at real-world projects already online. We'll take a look inside China's incredible Micius satellite. We'll also dive into what major companies like IBM are building. We're moving into an era where quantum computing could break much of the encryption we rely on today. The quantum internet isn't just a cool upgrade. It's a necessary defense against a new kind of threat. The race to build it is on, and the outcome will define the future of digital security. To understand the quantum internet, we first have to talk about its most basic piece of information. The classical internet is built on bits. A bit is super simple. It's a 1, it's a 0, an on, an off, a light switch that's either up or down. The quantum internet uses a qubit. Now, a qubit can be a 1, it can be a 0. But here's the mind-bending part. It can also be a 1 and a 0 at the same time, both at once. This weird state is called superposition. Think of it like a spinning coin. While it's spinning in the air, it's not heads and it's not tails. It's in a state of both possibilities at once. Only when it lands, or when we measure it, does it have to choose. It can become heads, a 1, or it can become tails, a 0. Two classical bits can only be in one of 4 combinations, but 2 qubits in superposition can hold all 4 of those combinations at the same time. Physicists can use tiny, individual particles to act as qubits. A single particle of light, a photon, is a popular choice. We can use one of its properties, like its polarization, to encode information. Okay, so we have qubits. But this next part is where it gets truly bizarre. It's a phenomenon called quantum entanglement. Einstein famously called it spooky action at a distance. Entanglement is when you take two qubits and link them together. Their fates are tied together, no matter how far apart they get. You keep photon A in your lab in New York, and you send photon B all the way to a lab in Los Angeles. Whatever result you get for photon A, you will instantly get the opposite result for photon B. If you measure photon A and it collapses into a zero, at that exact same instant, photon B in Los Angeles has collapsed into a 1. This shared secret is the foundation for something called quantum key distribution, or QKD. By measuring a long stream of entangled photons, two parties, Alice and Bob, can generate a perfectly random and perfectly secret key that was never transmitted. But what makes it unhackable? It's called the observer effect. In the quantum world, the very act of looking at something changes it. It's like a tamper-proof seal on a medicine bottle. If the seal is broken, you know not to trust the contents. If Alice and Bob detect any errors, they know their channel has been compromised. They simply discard the key they were building and start over. So, what do you need to actually build one of these quantum networks? First, you need a source that can produce single photons. Next, you need a way to send these fragile photons. Finally, you need an incredibly sensitive receiver. This combination of ground-based fiber and space-based satellite links is likely how a future global quantum web will be constructed, creating a hybrid network that spans the entire planet. But this isn't just theory anymore. It's happening right now. And the most dramatic proof of this comes from China. In 2016, they launched a satellite named Micius. First, a quantum-secured video conference. Beijing, Vienna. The satellite generated and distributed a quantum key. That key encrypted the video call, unhackable. In another experiment, it sent entangled photons to 2 ground stations in China. The stations were over 1,200 kilometers apart. The particles stayed entangled. The success ignited a new space race. China's rapid progress has shown the world what's at stake, pushing other nations to accelerate their quantum ambitions. While China was looking to the stars, another giant of the tech world was tackling the problem from the ground up. I'm talking about IBM. Inside IBM's quantum labs, it looks like something straight out of a movie. Dilution refrigerators used to cool quantum processors to temperatures colder than deep space. It's one thing to send a secret key, it's another to link 2 quantum processors so they can work together as one. Their goal is to build the quantum equivalent of the Ethernet. They've already demonstrated the ability to link processors within the same lab. The next step is to connect systems between different buildings and eventually different cities. Across the Atlantic, the European Union has launched its own massive coordinated effort. It's called the Quantum Flagship, a 10-year, €1 billion initiative. It brings together academic researchers, industrial partners, startups, to build a pan-European supply chain for quantum hardware. But there's a big problem with using fiber over long distances. As we mentioned, photons get lost. The solution is a device that sounds like science fiction, a quantum repeater. It uses entanglement to teleport a quantum state without ever directly measuring it. It's like a relay race for entanglement where the baton is passed without anyone ever looking at it. Building a working quantum repeater is one of the biggest challenges. A leading physicist in the field called it the holy grail of quantum networking. So, with all this incredible progress, when can you expect to log onto the quantum web from your phone? Think of it like the classical internet in the 1970s. Current limitations are significant. The biggest issue, distance and speed. Next, cost. Equipment is still incredibly expensive. At first, the biggest impact won't be in your home. It will be in the background, securing the most critical pillars of our society. Imagine two world leaders needing to have a conversation. With a quantum network, they could generate an encryption key that is provably perfectly secret. Any attempt to eavesdrop would be instantly detected. The first consumer applications will likely be invisible upgrades to the services you already use. The result for you is simply a safer banking experience. It's a security upgrade that happens completely in the background. Beyond just security, the quantum web promises to unlock entirely new possibilities, creating a network of quantum computers. This could supercharge scientific discovery, designing new drugs, designing new materials. It would also create a new kind of telescope, letting astronomers see distant planets with unimaginable resolution. A leading physicist called it a new sense, letting us see the world with quantum precision. Whenever a technology this powerful comes along, it doesn't just change our devices, it changes the world. We are already seeing the beginnings of a quantum arms race. This could lead to a splintering of the internet. We might see separate, non-interoperable quantum networks controlled by different geopolitical blocks. The central promise remains as powerful as ever, but we also have to be realistic. This is a marathon, not a sprint. The journey requires patience and sustained investment. They are the ARPANET of this new age, proving the principles and laying the foundation for the infrastructure that will define the 21st century. The promise is real, but it will be built piece by piece. Let me know what you think down in the comments. Is the quantum web the future or just science fiction? I'd love to hear your thoughts. As always, thanks for watching. You're watching Apex Tech, decoding the tech that's building tomorrow.